In terms of stellar properties, the fundamental attribute of a star is its mass. Mass determines everything about a star, from what type of fusion process can occur to its fate and eventual endpoint. Mass is actually the hardest thing to measure directly for a star, for an isolated star can only be done through a stellar model. But luckily many stars are in binary systems, and the binary orbit and the parameters of the orbit give the mass of both components. In nature, the bounds on star mass are about 8% of the Sun's mass at the low end to roughly 100 times the Sun's mass at the high end. Second fundamental property of a star is its luminosity, how many ergs per second or watts that it puts out in a particular wavelength regime. Or overall, across the energy spectrum, this is called bolometric luminosity. The luminosity of stars on the main sequence, which is to say stars that are fusing hydrogen into helium as the Sun is, has an enormous range, going up to about 1,000,000 times the luminosity of the Sun, down to about 1/10,000th of the luminosity of Sun. So this is a fundamental attribute of stars. Their mass ranges only by a factor of 100, where the luminosity ranges over a factor of 10 billion. The other direct observable quantity of most stars is their temperature. But it's important to remember that the temperature we talk about is the surface or photosphere temperature, the cool outer region where radiation travels freely to the observer. The true action is taking place deep in the stellar core at a temperature thousands of times higher, typically millions of kelvins if hydrogen is fusing into helium. Stellar photospheres range from cool red stars with temperatures of 3,000 Kelvin or so, maybe lower, to extremely hot blue-white stars with temperatures of 50 or 60,000 Kelvin. Because astronomers are able to take spectra of stars to decide what they're made of, they also classify stars in terms of spectral types. In this categorization, the Sun is a G-star. What is it that determines the range of stellar properties? And why are there bounds at either end, in particular in mass? It turns out that nature puts a limit on the mass of a star, both at the high and the low end. So it's not possible to have stars that are the mass of a galaxy, nor is it possible to have stars that are the mass of the Earth. The lower bound on a star is essentially the size at which the central temperature never gets to the point where it can fuse helium from hydrogen. This corresponds to about 8% of the mass of the Sun. Stars around this mass can actually do a feeble amount of deuterium burning, which is the first of the 3 steps of the proton-proton chain, where protons are fused to make a proton-neutron combination called deuterium, or heavy hydrogen. This releases rather a feeble amount of energy. Substantially higher temperatures are required to create helium. So, while nature may indeed collapse clouds of gas that are 1% of the mass of the Sun, or 0.1%, or 5%, those clouds will get warm and hot in their interiors, but never hot enough to switch on like light bulbs and be stars in the sky. The upper bound on mass is a little less well determined and requires computer simulations and theoretical calculations to understand in detail. But basically, if a gas cloud more than about 100 times the mass of the Sun collapses, it does so violently and catastrophically, essentially disrupting itself before a stable object is able to form. Nature, therefore, does not seem to be able to make stars much more massive than the Sun. Given the difficulty of determining star masses when they're isolated in space, nobody's exactly sure of the upper mass bound on a star. Various published numbers include 150 or 160 or 170 solar masses. These are exceptionally rare objects in any case. As a result, there is only a range of a factor of 1,000 of stellar mass. These stellar masses accrue to the other stellar properties. In other words, the star just under 1/10 the mass of the Sun is a feeble emitter of radiation, 10,000 times feebler than the Sun, whereas the star 100 times the mass of the Sun is prodigiously creating energy at a rate millions of times that of the Sun. Similarly, the low-mass stars are extremely cool and glow dull red, whereas the highest-mass stars are extremely hot and glow white or even blue-white. These colors are actually visible in the sky and to the naked eye, and they truly represent the color of the photosphere of those stars. Based on the mass of the star and its fusion process, stars reach an equilibrium size. The most massive stars are also very large, and also stars that are fusing heavier elements than hydrogen into helium attain even larger equilibrium sizes. Most people are unfamiliar with the enormous range and the size of stars. In this animation, a continuous zoom shows us the relative size of the planets compared to the Sun, and then moves on out to even larger stars than the Sun, ending with the largest red and blue supergiants, whose sizes are literally tens or hundreds of thousands of times that of the Sun. How long does a star last? Intuition fails us here. We might imagine that a star more massive than the Sun has more fuel, and so should last longer, while a star less massive than the Sun has less fuel, and should die sooner. It turns out to be the opposite. Round numbers can give us the life expectancy of stars compared to the Sun. For reference, the Sun's total main sequence lifetime, which is the time that it spends converting hydrogen into helium by the fusion process, is about 10 billion years. If we take a star 10 times the Sun's mass, by no means the largest possible, but a typical high-mass star, it has 10 times as much fuel as it starts its life. But its luminosity is so high that it's consuming that fuel 10,000 times faster. 10 divided by 10,000 is 1,000, so its lifetime on the main sequence is 1,000th that of the Sun, 10 million years. In detail, and for higher mass stars, the main sequence lifetimes get close to 1,000,000 years, a phenomenally short time, similar to the time of evolution of humans on this planet. Indeed, there are stars in the sky that are so massive and newly formed that they formed after humans did. What about a feeble star, a less massive star, a red star? A star at the low end of the mass sequence, about 10% of the mass of the Sun, has a fuel tank 1/10 the size of the Sun's. But it uses its fuel at 1% of the rate. So using those two numbers, it actually lasts 10 times longer. Instead of 10 billion years of main sequence lifetime, it has 100 billion years. Again, in detail with stellar models, total main sequence lifetimes at the limit of the fusion regime are hundreds of billions of years. These stars are essentially eternal. If stars like this formed even soon after the Big Bang, they won't die out for millennia, for eons, literally. So in general terms, we have a situation where the high-mass stars are high luminosity, short-lived, large, and blue, at their photospheres at least, and low-mass stars are low luminosity, long-lived, small radius, or small physically, and red, or cool, at their photospheres. These are just main sequence stars, stars converting hydrogen into helium. There are stars at different phases of their lifetime that are doing different things, and their properties are related in different ways. We'll talk about them later. For example, there are even larger stars than the Sun, or even than a hot blue main sequence star, that are near the end of their lives converting other nuclear fuels. There are also exceptionally small stars, smaller than any red dwarf main sequence star, that have lost their energy support, are not conducting fusion, and have collapsed to new states of matter. Stars span a range of roughly 1,000 in mass, from 1/10 the mass of the Sun to about 100 times the mass of the Sun. And the mass drives every other attribute of the star, including its eventual fate. The highest mass stars are exceptionally luminous and large, and live for short times, whereas the lowest mass stars are feeble, red, and live essentially forever.